much appreciated. And thanks, Ollie, and to the organizers of the ICMS and the LMS colloquium here. The title is Hilbert's Hotel and Other Encounters with Infinity. Oops. Okay, how do we measure infinity is what we're going to start things going. And how do we compare infinite sets? If someone tells you that it's equally likely, whatever that means, for a prime number to have residue +1 as it is likely for it to have residue -1 when you divide by 4, in how many ways might you formulate a correct, rigorous statement that is in accord with that claim? Forget for the moment any proof of the claim, just how do you formulate it? Well, you're led almost immediately to what one might call density, because you have an infinite set, a subset of, say, primes that are congruent to 1 mod 4 in another infinite set, which is a set of all primes. And you might ask, what's the density of that subset? In particular, what's the density of any subset contained in an infinite set? What does that mean? And of course, before you even get to that, you have a prior question. What is an infinite set? So there is this marvelous residential hotel, Hilbert's Hotel, with, as I put it, an unending corridor of rooms. This is the picture. And by the way, I have a footnote here. Now, the footnote in this particular instance just gives credit to the picture. But very often there'll be footnotes which have sort of added references and so on. I don't expect you to see it as I do, as I run through these slides, but along with this, lecture and Q&A, I have notes which are slightly more extensive, and there are footnotes, and all the footnotes I'm going to be talking about will be there. So if you're ever interested in going further in any direction, consult the notes, which will be in the chat, I hope. And if not, on the website of this recorded lecture. Okay. Hilbert's Hotel is very convenient. It never is really fully occupied, because if every room is occupied, as I'm sure lots of you know, the idea of Hilbert is to have some new guest, when he arrives, just ask the manager to request that all the guests move to the next room in the corridor in sequence, leaving the first room free for that new guest. Now that is a clear indication that Hilbert has infinitely many rooms in his hotel. But we're back to the question of what does it mean to be infinity? And I'm going to give you 4 possible definitions of infinite set. They're minor variants of one another. And the first, due to Dedekind, resonates very much with that corridor in Hilbert's Hotel. In the Q&A, I'd love to chat. What do you think is the difference between these 4 possible definitions of infinite set? And before I give them, I want to recall concepts. I'm hoping that they're familiar, but here they are: injective and surjective maps. An injective map is a map from one set X to another Y that has the property that it says no two different elements in the set X to the same element of the set Y. So the synonym is one-to-one onto. Putting it in logical vocabulary, if X and X prime are different in the domain set, their values f of X are also different, i.e. no collapsing, and typical example. Okay, surjective is a map that has the property that every element in the range set Y is the image of some element under the map F. The synonym is onto. So here it is in logical language, and here it is in pictorial example. Okay. All right. Now, here are the 4 different candidate definitions of this concept infinite set. The first one, a set is infinite if there exists an injective mapping of it to itself that is not surjective. Of course, if it's injective and not surjective, it's equivalent to say it's injective, but not a one-to-one correspondence between S and itself, because an injective and surjective map is bijective. Okay. This is Dedekin's definition in his essay, Was sind und was sollen die Zahlen? What are and what should be numbers? Definition 2 is similar, but it replaces injective by surjective. A set is infinite if there exists a surjective map from it to itself that's not injective. Equivalently, it's surjective, but not, again, not a one-to-one correspondence between S and itself. Clearly, intuitively, you're not going to have any finite sets having such maps, either definition 1 or definition 2, but there they are, definition 1, definition 2, and here's definition 3. A set is infinite if there's an injective map of the set N of natural numbers into S. So the set of natural numbers, of course, is numbers 1, 2, 3, and 4. As I write here, even though the ancients were dubious about the number 1 as being the same category as the other whole numbers. But it's important to know that introducing the set of natural numbers into the scene requires a certain amount of serious logical apparatus, mathematical induction, whereas Dedekin's definition is straight there. Okay. Definition 4 is very similar. It replaces injective by surjective. The set is infinite if there's a surjective mapping of S onto the set of natural numbers. And we could also pass the buck by defining an infinite set just as an infinite set, that is to say a set that's not finite, but that does pass the buck because we're left with then the question, what is a finite set? So there we are with a whole bunch of definitions. This raises the question, whenever you do something in mathematics, are you defining something or characterizing something? I write here, within the appropriate axiomatic set theoretic context, these 4 definitions of infinite set are equivalent, but you have to be within an appropriate ambient set theoretic context. But within such a context, we have a choice. We can choose one of them as our primary definitions, and the other 3 can be thought of as equally pinpointing the same concept, but they're labeled from our point of view as characterizations of the already defined concept, infinite set. Or we could just throw up our hands and say, they're all equivalent. Anyone can serve as the definition. Okay. Now, the actual logical relationship between these choices really does depend on the ambient axiomatic context in which we're working. For example, if you accept the axiom of choice, then and you can prove this as an exercise, very easy. If a set is infinite following the surjective definition, it's infinite following the injective definition. And here, again, as I mentioned, if you want a really excellent account of these issues, you can go to the notes and find the link to this marvelous essay. Okay, so we always have in front of us for any concept in mathematics definition versus characterization. The question, what is an infinite set, depends upon the choice. And the same holds for the question, what are prime numbers? What are, I'd say, and what should be, following the tone of Dedekind's essay. So here are two possible definitions. A prime number P is a whole number greater than 1, first definition, that is not expressible as a product of two smaller numbers. It's unfactorable. Or that it has the property that if it divides a product of two numbers, it divides one of them, a kind of divide and conquer property. Your choice, you can choose. If you choose the divide and conquer type of definition as the fundamental definition, you're doing something more than just making a random choice. You're actually placing the notion of prime number in the broader context of primeness as it applies to number systems much more general than the ring of ordinary numbers. And more specifically, you're framing it in the context of prime ideals of a general ring. You're saying that a prime number is a prime ideal in the ring of integers. And that's definition 2. And once you've done that, the unfactorable definition, the definition 1, becomes, well, a specific feature that characterizes prime numbers. It's equivalent, thanks to the theorem that guarantees this equivalence between these two formulations. Or you could go the other route. You could focus on the unfactorable quality of prime numbers. And then the divide and conquer quality is simply a more general feature, which also characterizes prime numbers. Okay, so having asked what are prime numbers, we can now ask what prime numbers are there. And it's quite marvelous that there are new prime numbers discovered every few days. And 2 weeks ago, a record prime of 50,001 digits was computed. There it is. Very nicely described. I mean, you would think that prime of 50,001 digits would take pages and pages to, anyway, there it is. It's the smallest prime of 50,001 digits. And here's the reference if you want to follow that. And then we also have proofs that there are infinitely many prime numbers. The classical one is Euclid's in his Elements. And I always keep wondering elements. Stoicheia is the Greek word, and it's a pretty stark title. Nobody talks about this. Elements of what? Anyway, there it is. Euclid's proof. I hope some of you have seen this before. What it does prove is that the set of prime numbers is non-finite. That is, say, you give me any finite set of primes, for example, the first 5 of them, 2, 3, 5, 7, and 11. And you just multiply them all together and add 1, and you realize that 2, 3, 5, 7, and 11 doesn't divide that number. And that number is divisible by some prime or other. And so therefore there's another prime not on your, not on that list of primes you have accumulated up to that point. In this case, that product plus 1 is in fact a prime, but of course there are others way before it. More fun are some far out proofs, and I just dreamt them up for this lecture. I dreamt them up because there's going to be a Q&A, and I'm interested in people's reaction to it. Well, here's a far out proof. We're starting with the Riemann zeta function, and I put an S there, and I'm talking about complex numbers whose real part is greater than 1, but nothing that I'm going to be discussing this whole hour requires S to be complex. You can just let S be a real number, and everything I want to say is that's all I need. So the Riemann zeta function is expressible as the sum of the value of the zeta function at any number S is expressible as the sum of the reciprocals of the S powers of all integers. And Euler noticed that it also has an infinite product rather than an infinite sum description over primes, and the product of all primes of 1 minus 1 over p to the S inverse. And to move from here to the other, from here to the, well, from the sum, infinite sum to the infinite product description of the zeta function, all you need really is the unique factorization theorem and a tiny bit of calculus. A little more than a tiny bit of calculus is a theorem of Euler. Euler computed the values of the zeta function at positive even integers. So for S equals 2n and any positive integer, Euler proved that the value of, the zeta function at 2n, which I could write in terms of that infinite product description, if you want, is a rational number, a positive rational number, times the 2nth power of pi. And that rational number, it doesn't matter what that rational number is, it happens to be a simple number times the 2nth Bernoulli number. Okay. So what if there were only finitely many prime numbers? If there were only finitely many prime numbers, then this product over all primes will be a finite product of rational numbers, which would again be a rational number. So that's a contradiction, right? Because we have this equation where we have zeta 2n is this infinite, well, is this product, which we're assuming it's finite, is a rational number times a 2nth power of a transcendental number. That's an irrational number. But of course, I'm making use of one of the great classical theorems that pi is a transcendental number. So choosing n to be any number, any positive number you like 1, 2, or a million, you get a contradiction from this equation. Oops. Oops. Well, I don't know what I'm doing here. Yeah. Okay. Yeah. Because you're never going to get an irrational number equal to a rational number. So for any choice of integer n, we have as corollary, there are infinitely many prime numbers. I'll call that proof sub n because it depends on n. For any n, you get such a corollary. Now, I have a query. Well, I call it query because it's not a specific mathematical question. I just want to begin musing about these things. Assuming that these proofs aren't circular, and they certainly aren't, I think, would you consider them to be different proofs for different choices of positive integer n? In other words, do we have infinitely many different proofs? And the other question is even sort of more relevant to the four definitions, 4+ definitions of infinite that we talked about a few minutes ago, which, if any, of the definitions we listed above of the concept infinite, do these proofs rely on? After all, if you prove there are infinitely many x's, you would think if you're working logically, you had better have in mind what the definition of these terms are. Anyway, these are queries. Since we're talking about prime numbers, I want to talk about prime number races, and that's the title of a really great article by Granville and Martin. The footnote gives the link to it, that explains in detail the race between the team of prime numbers congruent to 1 mod 4, and I'm going to color them blue, and the team of prime numbers congruent to -1 mod 4, and I'm going to color them red. Now, that goes back to the first question I asked at the very beginning of our session. So there's red versus blue. So here are the first, well, the prime's less than 100 and colored appropriately, and of course 2 is out of the game. But 3 is congruent to -1 mod 4, and so it's red. 5 is congruent to +1 mod 4, so it's blue. 7 is red, 11 is red, and so on. So that's the race. Primes congruent to 1 mod 4, the blue ones, versus primes congruent to -1 mod 4. The score so far for those primes less than 100, there are 11 blue ones to 13 red ones. They're a tiny bit more primes congruent to -1 mod 4 than primes congruent to +1 4. Right, race is very close. The primes congruent to -1 mod 4 is ahead here. And that's often the case for larger packets of prime numbers. So the score for primes less than 100,000, there are roughly, I don't know, 9,500 such primes. And half of them pretty much are blue, half of them are red, but there are something like 15 more red ones than blue ones. It's a very tight race. If you flip a coin and you choose a prime at random and ask, what's the probability that you've got a prime congruent to -1 mod 4 or +1 mod 4? The answer is a half, and that's a theorem of Dirichlet. In fact, more specifically, one can say the ratio of the number of red primes less than x to the number of blue primes less than x, that ratio tends to 1 as x tends to infinity. The race is tight. It's even tighter given a conjecture and a theorem. The conjecture is that for 100% of the positive integers, the number of red primes less than x beats the number of blue primes less than x. That's a conjecture. But there's a theorem of Littlewood that goes the other way, sort of, that says that there'll be cutoffs that are arbitrarily large for which the number of blue primes less than x exceeds the number of red primes less than x. And the footnote gives places to look for more discussion of that. So this discussion might lead us to this general question. What ways are there to measure the density of a subset S of the set? I'm going to call it script P of prime numbers. Well, at first, of course, such a notion, density, it should at least be defined on lots, but not necessarily all subsets of prime numbers. It's sort of like measure, certain subsets of the plane are measurable, some are not. One hopes that the ones you're interested in are measurable. Well, not all need to even have a definition. So to every subset of primes, there'll be its density, I'll call it delta of S, and it's the density within the context of all primes. So it's a number between 0 and 1, a real number between 0 and 1, and it should have at least these basic properties. The density of all primes, that should be 1. It's a set S is of density 1 in itself. Yeah. The density of any finite set of primes is 0. And the density should be finitely additive. That is to say, if you have S1 and S2, two subsets that are disjoint subsets of primes, and you let S3 be their union, if 2 out of these 3 subsets have defined densities, then the third one should also have a defined density, and the density of the S1 and the S2 should add up to the density of the union. That's the perfectly reasonable requirements, if you wish, if not even axioms for a density function. Now, there's something called natural density, and it certainly is. In fact, it's the type of density that I alluded to earlier in terms of red and blue. The most natural density you can think of that could be called the density of a subset of primes is you take these fractions, the number of primes in that subset less than or equal to x, let's say, and divide and take that number and divide it by the number of primes of all primes less than or equal to x. And then you let x go to infinity. And if that limit exists, you define it to be the natural density of S. And this natural density satisfies all the requirements in the axiom above. Of course, there'll be some sets that will elude that limit, will not have a limit. There's one thing to notice, which is rather important, I think, in trying to get one's head around all these issues of density. The natural density, it depends on very little. It depends only on the structure of this set P viewed as some abstract ordered set, and not at all on the placement of these prime numbers within the set of real numbers, not the fact that they're prime numbers, and Also, if you're willing to replace lim by lim, you would even get a definition. I like to use the word proportion rather than density, which, and I put an underline there, of any subset of natural numbers T using this natural density format. That is, say, number of elements in your set T less than X divided by the number of elements less than or X, which is X. If we're running through and letting X range through positive integers moving to infinity. So anyway, given that, here's something that's not yet a density. And I'm going to consider this because I want to compare this, the natural concept of proportion of subsets of prime numbers and the set of all prime numbers with notions of density of primes that in fact depend on the actual positions of the primes in the number line. That's sort of already sort of unintuitive that you might be willing to do that. The density of a subset of primes, why should that depend in a specific way? In any case, you give me a real number, x greater than 1, and any set of primes, s. And this is a made-up word for this lecture. Let's define the x density of s to be the ratio of the x power of the reciprocal of primes, the sum of them, all of them in the set S, that's in the numerator, all primes in the set S. So I'm assuming that this could be an infinite set, over the sum of all primes whatsoever of reciprocal x powers of those primes. Now, notice, in order to make sense of this, you have to know that both the numerator and the denominator do converge, whether or not there are infinitely many or finitely many primes. And we know there are infinitely many. And that they converge, I leave that to you. Same calculus exercise will get you to see that. The numerator and the denominator converges for any real number x greater than 1. So what's neat about this x density is that it is defined for every subset of P, and it's finitely additive. It does have one big defect, though. It assigns a non-zero density to absolutely every non-empty subset, including finite subsets. So any non-empty finite subset has a non-zero x density, which is surprising, or annoying rather than surprising, I should say. But here's a way that Dirichlet used to correct that defect. We're going to get something called Dirichlet density. You define the Dirichlet density of any subset to be the limit of its x density as x tends to 1. So Dirichlet density is the limit of delta x of s as x tends to 1, if that limit exists. So you notice that if S is any finite subset of primes, this numerator of the equation has a finite limit as x tends to 1. But the denominator as x tends to 1 goes to infinity. So the Dirichlet density, which is the ratio of something finite over infinity, of any finite set of primes is 0. And then you see that the Dirichlet density satisfies all three requirements desired for a density that I listed before. So Dirichlet density and natural density are two ways of measuring the density of subsets of primes. Happily, we have this theorem that if a subset has a natural density, then it also has a Dirichlet density, and the two densities are the same. Now, what does that give you? Well, in certain instances, in many instances, in fact, probably most instances, the Dirichlet density is much easier to compute than natural density. So you compute its Dirichlet density, and you then immediately know, well, if it has a natural density, if your set has a natural density, you know what it is at least. Now, Dirichlet's theorem about the red and blue primes tells us that if we pick primes at random, we'll get primes of residue +1 rather than -1 on 50% of the time. And of course, the other way too. If it has a residue of -1, that'll happen 50% of the time. Dirichlet proved a much more general theorem. He proved that the same sort of thing is true for any other reasonable congruence condition. That is, say, a condition that distinguishes primes by how they behave modulo m for any fixed integer m, not just 4. So take m, be any positive number. And x is phi of x. That is Euler's phi function. That is, say, the number of integers less than x that are relatively prime, positive integers less than x that are relatively prime to x. So if m is a particular integer, we have phi of m congruent classes containing elements relatively prime to m. And given such a congruence class, you might ask, what primes fall into that congruence class when you reduce them mod m? And Dirichlet showed that the probability that a random prime falls into that congruence class is exactly 1 over phi of m. That is to say, the primes are uniformly distributed, just equally and uniformly distributed over those congruence classes mod m. Okay, I don't want to end this discussion with a theorem that's proved, quite a while ago. How about a theorem that is just proved last month? A very new, interesting theorem about proportions of numbers, about densities of numbers, or proportions of numbers having interesting properties. So the question is, what is the proportion of integers that are the sum of two rational numbers that are cubes, rational cubes? And if you try to play with this, you see that this happens pretty frequently. One, of course, is 1 cubed plus 0 cubed, so that doesn't count. 2, similarly, 6 begins to be interesting. There it is. Is it likely that an integer is the sum of two rational cubes? As not. Now, a very recent result of Alpoj, Bargava, and Schneidman, and there are full proofs forthcoming. There is in the slightly revised notes, I'll be giving complete references. They haven't yet put it on archive, but they've given me they said I can announce this is a positive proportion of integers are not the sum of two rational cubes. This is entirely written, and a positive proportion of integers are is their theorem, which I think is one of the really beautiful, surprising, and as recent as you can imagine, proofs in the field of arithmetic statistics. So welcome to that field. The types of questions, density type questions are utterly traditional, as I indicated by Dirichley's work, but also are in currently burgeoning, rapid moving part of number theory, the aim being to get the statistical lay of the land regarding basic issues in number theory. So I hope we'll have a good Q&A regarding all this.